Morning. Let's get started. Yeah, so today we're doing an in-body problem. I think everybody knows we have an exam Wednesday. This will not be on the exam, but it will be on the next homework, which will come out sometime later today. So yeah, if you have any questions about the practice problems, please let me know. And yeah, we will start at 8 on Wednesday. Any issues? All good? Yes.
Do we get a cheat sheet kind of thing for this exam?
Yeah, like the same as before. You can do one regular size paper front and back. Yep. Anything else? Yep. Okay, cool. So today we will do, like I said, we're doing to learn the n-body problem, which is, I thought this was kind of cool. I was learning over the weekend. And so the motivation is that at a high level, like these days, we do a lot of computational simulation on supercomputers, on regular machines, whatever it is. And because things, like I said in the beginning of the class, some things are too hard to actually measure or run the physical experiments on, so we do discovery using computational simulation. And often these computational simulations can be really big, like several million variables or even more, so they need to be fast. And most large problems, like we saw in FFT, they boil down to like matrix vector product. And they are different kinds of matrix vector product, like FFT has a specific structure. And I see n-body as kind of similar to FFT in the sense that it is like matrix vector product, but with structure, but with a different kind of structure than FFT. And like from last time, if you just naively do the product, it will take n squared time and accuracy. So like the simulations that we're trying to do, often like we have these points and they exert some kind of force on each other, like gravitational force or electrical force. And we have physical equations to describe the force that every point exerts on every other point. We can just sum them up, but that would of course take n squared time because every point would interact with n other points, which is computationally not going to happen. And yeah, so there are these really clever methods that work on divide and conquer, and they can drop down the cost to n log n or even order n. And the high level intuition behind these methods is basically that you only have to do the exact calculation for things that are close to you, and you can do approximations for things that are far from you. So these are approximations, but they get you really close to the true answer, and usually the approximations, like you can set a parameter for what accuracy you want, and usually like the more accurate it is, the more expensive it's going to be, and vice versa. Yeah, but in asymptotic notation, it's usually like log n. Okay. So like I said, the high level intuition is that you compress this far away data for some definition of far away into one point. So like you have many points that are far away from each other, and you in some sense like you take the average of them, both in terms of average force and also like center of force or center of mass. And you can cut out a lot of the computation. Like the cheapest work is the work that you don't have to do. So you do some pre-computation where you average out a bunch of the far away points, and then you just do like one single computation on your nearby point, or like you have one point under consideration, and you're trying to calculate the force from n other points on you. And like you take the far away ones and you group them whatever they are, and then you just do one single addition or multiplication or something onto your own point to approximate the force from far away. And some examples of applications seems like a sort of intuitive idea, but it shows up in a lot of places. Elliptic PDEs, the main one that it shows up in graph partitioning, and the main one that we're going to do today is for n-body simulation, like physical simulations. So two famous methods are called Barnes-Hutt and fast multiple method. And you may have heard of these because they're classical methods and really nice. This is the general workflow for a particle simulation. So you have some time t, and you're just doing time steps. And while your time is less than some final time that you're going to run your simulation for every particle that you have, let's say you have n particles, for I1 to n, you compute the force on particle I through some equation. And then after you've computed all the forces, you say, okay, like how does this affect my position in the next step? So for example, like movement. If you have xy coordinates, you have some acceleration and velocity, and you can calculate the next position in the next time step. And then maybe you compute some other properties as well. Potentially you update your time and you just go back to the beginning. And the most expensive part of this was this, which is kind of hidden, Naively, it would follow this equation, which is f of I for every I is the sum over all points that are not I, k not equal to I, of the force of I, force on I from k. So it's like this. And trivially, this is going to take n squared work because you can just compute this directly. You have all k positions. You have some equation to dictate how they affect each other, and you can just go through and calculate them. And also, this is easily parallelizable. Like all fi are distinct, so they don't depend on each other, and you could imagine like partitioning up your points separately, and just every processor is responsible for some n over p points. But we want to reduce the work from n squared to something much better. And here's some more motivation. Again, FMM, sorry, fast multiple method, was in this article from the top 10 algorithms from the 20th century that they wrote in 2000. And it is frequently used in scientific computing. So this is the same diagram that we had before. And last time we were doing FFT here, and today we're doing n-body simulation, which is there. So n-body simulations take up a lot of cycles on supercomputers. Yes.
How do you think that graph of those most commonly used algorithms has changed in the past 20 years?
It's a good question. Now it's probably I mean, maybe dense matrix has become almost all of it because machine learning is built. Machine learning was originally built on dense matrix calculations, and now they're trying to make it cheaper. They're trying to build it on sparse matrix calculations, but it's not so easy. So probably in the past like 5 years or so, this has become the major thing. Most like these are kind of more traditional, like n-body simulations are really popular like in the 80s or so, but they're still nice methods, so I think we should still learn them. But I think they're less popular now than matrix calculations. But these are all they all have nice algorithmic ideas. So whether or not they fall in and out of popularity, I think it's still worth it to do them. And often like techniques from one, they kind of like bleed into each other a little bit. Yeah, good question. And some of them like are somehow easier. Like dense matrix calculations, it's sort of like maybe like the most classic problem in this list. And like some things are harder or easier in the sense that like this one is more computation heavy, and this one like graph traversal is less computation heavy but more about memory movement. So they're like some of them are pretty different in terms of the character of the problem. Thanks. Cool. So a couple applications for these n-body simulations. Classic one is astrophysics, like you want to compute something about planets or stars, and you have, so this is an example, in 1992, they computed a simulation with 17 million particles with 600 time steps, and it took them 24 hours. And they won the Gordon Bell Prize, which is like the highest prize in high performance computing. I mean, this is a long time ago. This is 1992, but still, back then, they were able to do 5.2 gigaflops, which is a huge deal back then. Now we have supercomputers that can do exaflops, but it's not that every algorithm is going to achieve an exaflop on the supercomputer. Like you have to, it's that it can sustain it, but you have to tune your algorithm to do it. And yeah, and just for comparison, like if you did the direct method of doing n squared calculations, it would have taken 18 years. So this is the power of algorithms that you can do just with, like you can significantly cut down the time just by doing slight approximation. Another example, maybe more popular on GPUs, is 2009. So that was still, in 2009, like GPUs still hadn't really become as popular as today. Nowadays, like everybody is trying to write on GPUs. But they were able to do more particles, like 16.8 million particles, and they won the Gordon Bell Prize in 2009. And they were able to do 20 teraflops on a system of GPUs. So yeah, pretty cool. So this is a high-level picture of what these divide and conquer algorithms look like. All of these algorithms kind of follow the same intuition, which is, suppose that we have an example of a bunch of galaxies, and we want to compute the force on Earth due to all the other, due to all the bodies in space. And if you look at them, we cannot directly calculate the cost of like every star's effect on Earth, because that would be computationally hard. And um, and within each of those, like if you look, like in this example of the galaxies, if you look at the sky, there's so many stars, and each one of those stars is actually a galaxy within them. So it's not that there are many stars, and like you can still calculate the effect of every star on you, but it's not just those stars because each of those have bodies inside of them. So it gets even worse. And um, the intuition here is that it's fine because if they're so far away, you can approximate all the stars in some galaxy by computing the center of mass and the total mass. In the center of mass, like you have a bunch of points and you just, you average them out. You average out their positions, and total mass, you just add up their masses. And so you approximate like a galaxy with one single point. And yeah, and the main parameter here uh, is it's like r, which is what is telling you how far, like what is far enough to do this approximation. And so when you actually think about doing this in a computer, you have some box, you have some bounding box in terms of your representation that is containing all of the points in this galaxy, and then you have some distance between your point of interest and the bounding box that you are trying to approximate. And if it is farther than some specified distance in your parameters, then you can do this point approximation, which is of course way cheaper than doing that. But notice that you had to pre-compute the the center of mass and the total mass. And one question is, how do you cut up these bounding boxes? And we will do that in a little bit. Question? So if you just did this at one level, like suppose the highest level at the galaxy level, that would save you a lot of work. But um, the high level idea, like I said, behind these algorithms is that you apply this idea recursively. So, um, and also it's also like you want to do n-body simulation, which is that you want the effect of all points onto all other points. So it also happens in the reverse, which is like you want to compute the effect of the Milky Way, which is like where Earth is on every other galaxy. So Earth also has a bounding box. And within the galaxies, also the picture repeats itself, like you do a divide and conquer, and now you cut it into this smaller world. And these in the smaller world, now you also have smaller bounding boxes, and some of them are far away, and some of them are close, and you apply the same approximation to the ones far away. So you have to pre-calculate a bunch of these approximations, because like it's not just at the highest level. You cut it into bounding boxes, and then you pre-calculate total mass and center of mass. You have to recursively divide and conquer cutting your boxes, and then calculate the approximation for each one. Any questions so far? Yes. Yes, thank you. We will do that in a moment. Yeah, thank you. Yeah, so next we're going to do these classic data structures for particle simulation, but they can be used in many other things. The data structures are called quad trees and octrees. Maybe you already know about quad trees. So in 2 dimensions, we use quad trees. And basically the way it works is that you have this 2-dimensional plane. And at each level, you cut every tree, or like at each level, every node has 4 children. And every child is one of the 4 quadrants. So like upper left, upper right, lower left, lower right. And you can order them however you want. You just have to know which one is which. And you can see that, and it happens recursively. So in the upper left quadrant, we would cut this again into 4 pieces. So like the first cut is blue, this one, and then the next one is red, like this one here, and the lowest one is this light blue, like here. You recursively cut the quadrants, and in a full quad tree, every level has 4 to the I children, where I is like starting from 0. Yeah, and they can contain, of course, they can contain the points that are in the partition. They can also contain other information, like we were saying, we have to pre-compute things like center of mass and total mass, and you can also store those in the nodes. Like if you just imagine programming it, you would just add another variable for that. And in a complete quad tree, yeah, like I said, every node has 4 children except for the leaves. And if the points were evenly distributed, like if they were uniform, then they would be approximately evenly distributed across these nodes. So the first step in all of these algorithms is to compute the quad tree on the points that you have. And that is going to tell us like that is going to help us to tell which ones are far and which ones are close. And it's pretty easy for points because the points are just like, infinitely small, so they can fit in the nodes. When I was learning performance engineering, we had to build quad trees for line segments, and that was super annoying because the line segments can cross some boundaries, and then they have to happen at the. So like for points, they can all happen at the leaves. But for line segments, like you can also do this. We did it for like line segment collision, and it was really annoying because sometimes it could happen in the internal nodes if they crossed boundaries, and you had to figure out what level they appeared in. But for points, it is simplified. They're all at the leaves. And the only things that you have to compute in the internal nodes is the pre-computed like center of mass and total mass. And octrees are just a similar idea, except in 3D. So each level is 8 children because you have your 3D plane and you cut it into 8 quadrants. Just 2 in each dimension, X, Y, Z. Yeah. And these are really popular for also on GPUs for like rendering and like imaging. So this is extending beyond n-body simulation, but it's a classic data structure, and maybe it's just one of these classical spatial data structures. Like I said, all the algorithms for n-body simulation, all the efficient algorithms for n-body simulation, you start by constructing the quad tree to hold all the points. And it's not always true that your particles are evenly distributed. It is easiest, of course, if they are, because then your tree is pretty full and you don't really have any issues with load balancing. Like if you imagine parallelizing over this thing, like the easiest way is you cut up the tree evenly and then you ship it off to your different processors, which is great if they are approximately even, but maybe they're not, and then you would get load imbalance. So there are a bunch of clever schemes that people have come up with to deal with that. And there's a variant of this data structure that is just not a complete tree. It's called the adaptive quad tree or octree, and it just subdivides the space if there are particles there. So like if there were, for example, if there's only one particle in this upper left quadrant, this tree here, let's say this was the upper left, it would just be cut off here. Like you would get no more children because there's no point in continually subdividing this tree if you have only one point there. So the only difference is that this tree is no longer necessarily complete, and it can, like the branches can have different height. Yeah. So like the easiest, maybe you can imagine like the easiest way to build this would be you start with an empty quad tree, and you go over your points, and then you call like if you had a function called quad tree insert, and you just call quad tree insert on every one of your points, and you dynamically build this tree. And this is of course going to take you if the height is log n, it's going to take you n log n because like the maximum depth you could possibly go is log n. You may have to like build out some of these branches, but that's just, or maybe you pre-make this tree and then you just follow the branches and then you put the particle wherever it's supposed to be. There are more efficient ways to build it, of course, but that's like clearly a correct way that would take n log n. Make sense? So the first step is you just put all the particles in this kind of structure, and then we have to efficiently find a way to do the pre-computation. So there's 2 steps, well, 3 kind of. One is that you build this quad tree. Second one is that you do this averaging of the force calculation or of the center of mass and the total mass. And then after that, you have to use those things that you pre-calculated to compute the force on every point from every other point, approximately. Yeah, so this is just an example. Yeah, I guess these 2 are the lower 2. So this one, and they just get cut off because there's no more things there. But these, they continue recursively subdividing if they have more things in that quadrant. And so like this one has only one thing. So this one, or these 2 only have one thing. So those got cut off there. And then this only had 3 children because there's nothing in this one. So you just continue branching if there is something in that subquadrant. And in practice, the leaves probably wouldn't have just one child or just one particle. They would probably have order one particle where that's some cutoff that you can tune. So the cost to build this thing, well, it would be like using this method that I just said, would be at most n, which is the number of particles, times the maximum cost of your quadtree insert, which is proportional to the depth of the quadtree. And if the particles are uniformly distributed, the depth would be log n, because you cut them in fourths every time. So that would be n log n. And then if you had an arbitrary distribution, the depth might be arbitrarily long. And if your depth is b, then the cost would be b times n. Questions so far? So first we're going to learn this Barnes-Hut algorithm, which is maybe one of the first efficient algorithms for this, and it solves this n-body problem in n log n time. And the Barnes-Hut algorithm, it has three main steps. First one is you build the quadtree, which we just went over. That's cost n log n. Second one is for each node in your quadtree, you do this pre-computation of the center of mass and the total of mass. And you could imagine doing this several ways, but any normal, like efficient way would take time n log n. So like a very efficient way to do this would be that a bottom-up way, like you compute all the leaves, you compute the center of mass and total mass for all the leaves. And if each one has order one particles, that takes you order one for each leaf. This assumes that you have the means to access all the leaves somehow. And the nice thing about that is they can all happen in parallel as well. And then, well, you can notice that the parents of your four children also depend, like the parents don't have any particles that the children don't have. Any node in the tree just encompasses all the particles in the leaves at the bottom of that subtree. So you can do this bottom-up construction, and you can avoid doing recomputation. Then you just like do some weighted averaging of what you have already computed one level down. It is order n log n to do that. Actually, that very efficient way that I said, it would be order n, because you just have to do order one for every node, and there are order n log n leaves, or sorry, there are order n nodes if the tree is uniformly distributed. Does that make sense? Like there are n leaves, n over 4, one level up, and so on. So you sum all of them up. That's order n. And then it costs order 1 to compute for every leaf because there's order 1 particles in it. And then the one level up from there is just combining 4 points. So that is order 1 for all of them, and so on all the way up. So that's order 1 for order n nodes, so order n, which is order n log n also. Doesn't have to be tight. And then for every particle, we traverse the quadtree to compute the point. And this part is like the hardest part, and it needs to be order n log n to not ruin the entire complexity. Yes. Oh yeah, I'm just saying that this O n log n is not necessarily tight, because the method that I just described, it just has to be O n log n. It doesn't have to be theta n log n. Because if we want the entire thing to be O n log n, then this just cannot be more than O n log n. The method that I just described of starting from the bottom and combining with all the children would be n. A less efficient way that achieves theta n log n would be like, one way to see it is that every particle participates in log n nodes. So if you were to directly compute the sums, like without doing this bottom up thing, like you just look at every node and you compute the sum of all the particles that are underneath that node. That way you can also compute the weighted, that way you can also compute the center of mass and total mass. Every particle participates in log n nodes in the tree. So that would be again n log. That would be exactly it, order n log n. Yeah. So that does not require this bottom-up approach. Like that could be top-down, because it would take order n work at every level of the tree for n log n. The smarter way, like I said, you start from the bottom and then you reuse the work that you've already done. That would be order n. But the most important point is that just has to be cannot be more than n log n. Um, mhm.
Does the ratio of distance to like size play into this? I'm kind of learning.
Yes, good question. We will go there in a minute. This makes sense to folks so far? So the hardest part, most complicated part, is after you've done this pre-computation, you have to traverse this quad tree to use the approximation on what is far and what is close. And the question, really good question is like, how does what is far and what is close affect the algorithm? And we will see that in a moment. And naturally, sort of naturally, like if you want a better approximation, it's going to take you longer. Okay. So this is the main core of this Barn-Tutt algorithm, which is to compute the force on every particle. And it goes node by node. So for every node in the for every node, which is just like a square in your quad tree, you approximate the force outside by doing this single point approximation. And it's accurate enough if the node is far enough away. And the criterion is parameterized by r, or sorry, by theta, I guess, because d and r, like d is the side length, which is given by how you cut the quad tree. R, you have the distance from the particle that you care about to the node that is determined by the node under consideration of the quad tree. And theta is just some error that you can tolerate. And you do some approximation if d over r is less than theta, which is the desired error bound. Here's a picture. So we built this quad. Okay, so this is your 2D grid, and we build this quad tree. And in the root encompasses every single particle. So that would be, in this example, 24 particles. And so we can just go level by level. So yeah, so suppose that we're computing the force on this particle. And by our setting of theta, these three quadrants are far enough away that we, oh yeah, and suppose that we pre-computed like the center of mass, like we said. So these three quadrants are far enough away that we're going to just use the approximation. So we do like order one work, this one, and that one. And within our own, so then we recurse inside our own quadrant, and that expands into this. Happens that two of them are empty, but this one has three. And again, by the setting of theta, this quadrant is far. Yeah, this quadrant is far. So we also use the center of mass approximation for that one. And then this quadrant is too close within this example setting of theta. So we just do direct calculation, which we can do, like we have physical equations that tell us what is the actual interaction between them. And yeah, that's how it works. Like you go level by level, and you just determine which quadrants are far and which quadrants are near. And doing the close ones doesn't hurt you because they would be order one because the way you cut the quad tree, like the leaves have order one particles in them. So you can see, like, for each point, you can imagine doing this for every single point. And there are log n levels, and you have to do order one far approximations per level. So that would be log n per calculation. You have n particles, so that would be n log n. Does that answer your question? Yeah, go ahead.
So does the definition of what is far change?
It is fixed up front when you run the simulation.
Okay, so if you have like a simulation where things bump together in the center, for instance, then they're just into squared at some point.
Yeah, it would be, yes. It would be, I guess technically the work is like n times b, where b is the depth of the quad tree. Mm-hmm.
How do you construct the tree in parallel?
How do you construct the tree in parallel? It's a good question. So well, one way to do it is that, okay, so here's an naive way to do this. You have all your points, and you know the quadrants. And in parallel, you can evaluate which quadrant everybody belongs to. and then you do some reshuffling. You can do this reshuffling in parallel as well. Like you do this count, you know how many belong in each quadrant, and you do some reshuffling so that everybody, like quadrant 1, quadrant 2, quadrant 3, quadrant 4. And that can also happen in parallel. And then you recurse on the 4 quadrants. Maybe not the fastest way to do it because you have to do this reshuffling. There are more clever methods based on what is called Morton ordering, which maybe I will include in the homework actually. I think I've been playing around with it. So Morton ordering is like, so the normal way to do this is like you have x, like every point is x, y, and they are laid out in some order. And you can imagine like maybe they're sorted by x, and then within, if somebody shares an x, then they're sorted by y within that. And that is like a very natural sorted order for these points, but that is a bit hard for this partitioning that we're talking about because like it's not necessarily true that things next to each other in this sort that I just described are going to be in the same quadrant. In Morton ordering, it's also called Z ordering. So instead of like doing, this is the thing that I just described is like row major. Instead of that, in Morton ordering, it's like a recursive Z. So you have like small z's, and then those become like one big Z. And then so in Morton ordering, if two, like you just find two partition, or like you define two partitioning points based on the endpoints of the quadrant that you have up front, and everything between those in the Morton order is guaranteed to fall within the quadrant. Whereas like in row major order, the quadrants would be like separated pieces. Does that make sense?
So what would you use the Morton ordering for?
The Morton ordering is to avoid reshuffling. Yeah, in the initial scheme that I described, if everything is laid out in row major, like you have just look at partition 1. Just look at like the upper left partition. You know the x and y coordinates that it falls between, and so you could identify, if it was in row major, you could identify segments of your array of points that each fall into partition 1, and you could, of course, shuffle them closer together. But that would require reshuffling, and you have to know how big they are, and that can happen in parallel too. Like that's not really a problem, but it does require this reshuffling at every level, because then it would recurse down one level. Yeah, it's a good question. Yeah, the easiest way I can see it. I mean, you can also like. I'm not sure that gets you a better theoretical bound. Actually, it might like this like You could call like the most naive thing, which is you initialize an empty quadtree and then you call quadtree insert every time, and that doesn't require any pre-sortedness of your points, and it does take n log n time because the height of this tree is log n, and you know exactly where in the tree you need to go based on the spatial ordering. So maybe the most simple ways like that. Oh, how do you do it in parallel like that? You could use locks, I guess. Like on the, so let's suppose that you had made just a bunch of empty nodes, like in the structure, and you just go down the tree, and you only need to insert into the leaves because nobody is actually, like no particles appear in the internal levels. The particles only appear at the leaves, and you just go down to the leaf, and a lock just tells you whether you have exclusive access on that node or not. And so if you're trying to insert into that node, you just take the lock, you insert your thing, and then you release the lock. So then you don't get write conflict. That's probably a very simple way to do it. Yeah, so that's how you do it in shared memory. To do it in distributed memory might be easier because if you partition the points up front, like if you knew, suppose you had 4 processors, and if you could pre-calculate which points go to which processor, you could ship away like the quadrants, and each processor would be responsible for doing its own partition. Another way.
When you're computing the distances, does each processor need to have the entire tree?
When you compute the, oh, I see. To do the far approximation, you just need to know the distance of the center of mass to the point that you care about. So in distributed memory, usually the schemes look like everybody has the top levels of the tree, and the bottom levels are partitioned away because the top level is like asymptotically smaller than the rest of them. And also the top levels are smaller because the internal nodes only hold the pre-calculated stuff like center of mass and total mass, whereas the leaves actually hold the particles. So the top levels are much smaller, so it's okay to replicate them.
Each processor would have like a different subset of the tree.
Yeah, so each processor would have like its own set of leaves and maybe all the internal levels. But all the internal levels are just the metadata at each level of center of mass and total mass. Question. Yeah, this is a really good question. Quadrant construction can range from simple to complicated. From a theoretical standpoint, maybe it just needs to meet n log n, but from a practical standpoint, of course, like it should be, if you're not careful, maybe it would compare to the time to actually, usually like when you actually run the simulations, the quadtree, you only have to construct the quadtree once, and maybe things might move, but things don't move that often. Like um, they don't move partitions super often, so most of the time is spent um, in the simulation itself, and in the force calculation. Yeah. Does this make sense? Okay, so here's just some examples from this cool blog that I found over there. And they did some experiments. So they did like this naive one, I guess, is the direct calculation and squared calculation. These three are Barnes Hut with different settings of theta. And the smaller theta is, which is the smaller error you're going to tolerate, the time goes up. And x-axis is the number of points. See that like the more the theta is, the lower the time is. Natural. Okay. And then the example, or yeah, so on the other axis, there's time, and then there's also error. So they calculated the average, so they have like a vector of size n, where n is like the thing that where like you have a vector of the length of the number of points you have, and they calculated the average vector distance between what you calculated with the naive method and with Barnes Hut, and you can see that as theta goes down, like the error is going down as well. In practice, I think for Barnes Hut, theta equals 1 is usually a reasonable value to choose. Questions on that part? Okay. So yeah, so we did Barnes Hut, which is the n log n method, and you might think like n log n is already pretty good, and it is. Like, of course, it's much better than n squared. But actually, the thing that won the top best 10 algorithms up until the top 20th century algorithms is not Barnes Hut, but it is fast multiple method, which is how you can get down to theoretically order n. And it uses a lot of the same ideas. Like it still uses quadtree, for example, and it still uses like far field approximation. So spirit-wise, I feel like they're very similar. It's just like in some of the details, they're a bit different. Yeah, and I got these slides from this talk here, which is also really good. Oh, I got most of them from there. This one is not. This is from Berkeley. Okay, so at a high level, this is the paper that it came from. A fast algorithm for particle simulation by Greengard and Rocklin. The first one is in 87, but there have been many follow-up papers since then. And the main differences from Barnes Hut is, so in Barnes Hut, you just compute, for every level, you compute the center of mass and the total mass. And the FMM computes the potential at every point. So it, in some sense, like it tries to optimize more towards accuracy as well. So in Barnes Hut, you just do this one single point calculation for the far field approximation. But here, by potential, I mean it also computes like a bit of an expansion to get better accuracy. And yeah, it uses more information than in each box. So rather than the single point approximation, it also, in some sense, like I'll tell you later more details, but like you kind of keep you keep several terms of an expansion, and that's how you improve the accuracy because it's, I don't know, there's more terms. So like the first term would be the single CM and TM, and then subsequent points would be like further refining this approximation. And then to maintain the runtime, rather than the FMM, it uses the quadtree, and it accesses a fixed set of boxes at each level. It accesses order 1 boxes at every level, and yeah. Barnes Hut, you build the quadtree does not depend on your choice of theta. Like the quadtree is fixed, but the number of boxes that you evaluate in Barnes Hut depends on theta. In FMM, it uses a fixed number of boxes, but the accuracy parameter changes the amount of information in each box rather than the amount of boxes that are evaluated. But like I said, like the they both depend on the quad tree. They both depend on this hierarchical decomposition, which is this cool idea in scientific computing. Yeah. So we have these points, and we want to compute. It depends on the application. Like for electrostatics, it would be like charges. You can also do it for gravitational forces, for many other functions. So you have points xi, and you want to compute the force F sub I of every other point on you on x sub I, for all x sub I. And according to some function gxy, which dictates like how the particles affect each other, some examples for this would be natural log of the distance in 2D or 1 over distance in 3D. And the naive way to do this, like I said, you compute for every point, you compute the force between I and j, and you have some force f sub j, which is the destination affecting you, and then you sum them all up. And that can be expressed with a matrix vector multiplication. Like the matrix is every entry ij is gxi xj, and then the vector that you get in is f sub j, which is the initial configuration, and you get out the effect, which is u sub I. So again, this is just like the same as before, but it's a bit more formal. So the direct computation would be order n squared steps, which is too costly, and we want to lower this. And yeah, so we bring the complexity to order n for some, here the accuracy parameter is called epsilon. And yeah, for some fixed epsilon, it brings the complexity to order n, but the amount of data that you have to store in each node is dependent on epsilon. So smaller epsilon means it's actually dependent on, I think it's like log of 1 over epsilon or something like that. So it's not a very strong dependence on epsilon. Like it's not like 1 over epsilon. So yeah, basically the way this works is that the higher your accuracy, the more terms you keep in the expansion. And that is what you're keeping in every node. But for any constant epsilon, that thing is also constant. So that's how you get, it's really leaning heavily on the big O here. Yes. Yes, U is the cumulative effect that all other points are having on point x sub I, and then F is the charge or the force coming from every other point j. Yes. This one? This is like the function that tells you how the points relate to each other. So like if you plug in xi, xj here, that tells you like how xi, xj interact. Yeah. And you can imagine like you could do, if you filled out this matrix, you would just do one single matrix vector multiplication to solve this for one step of your simulation. The FMM, it's based on 4 key ideas, most of which we have gone over, like hierarchical decomposition and far approximation, but they fit together a little differently in the FMM. Okay, so the first idea, as we have already done, is that you do this single point approximation for well-separated regions. This is like another picture of the same thing that we have been doing, which is you have 2 boxes, A and B, and you want to compute the effect of all the points in box B on all the points in box A. And you don't want to do this n squared calculation, so instead you boil box B down to one single point, which is center of mass C sub B, and F sub B, force, is just adding up all. So like for masses, that would be center of mass, and then you add up all the masses to get total mass. And then you do the same for A. And you do the single point approximation. You say, what is the effect of this center, C sub B, on C sub A, which is the center of A? And then, yeah, that reduced it down from n squared, where n is the number of particles in B and A, to 1. We had to do order n to compute this, like this approximation, to boil them down to one single point. But we're going to do the similar quad tree trick, which is you the leaves have order 1 things by how you get the quadtree. So this thing to do this reduction is order 1. Yeah. So you approximate this effect of C sub B on C sub A, and then you propagate it back to everything in A. And that is going to take you order n as well. But because this is big O, if the number of points in box B and box A is order 1, then this just becomes order 1 as well. Okay. Yeah. So what is the cost of this? Well, if A has n sub A points, B has n sub B points, originally it was going to take us n sub A, n sub B points to directly do the calculation. Now it's going to take n sub B plus n sub A points to convert them into 1 point, and then takes you just 1 step to actually do the effect calculation, but it takes n-ish points to boil down everything into 1 point. So this is similar to what we were doing in Barnes Hut. This has good enough accuracy if A and B are far away for some definition of far, and we will use it whenever A and B are well separated. Or well separated. Well separated is now, it's not necessarily, so there's no like theta parameter in the FMM. Well separated now only depends on the quadtree, which I will go into more detail about.
So in Barnes Hut, it was kind of like you compute like the effective B on every point in A, but this one just like generalize it to A and then apply that to all the points. That kind of the one.
Yeah, like in Barnes Hut, you can kind of imagine that the if you fix every point, like you fix a point and then you look at the path in the quadtree, or you look at the relevant node in the quadtree corresponding to that point, that relevant path search would be order log n. So like in both Barnes Hut and FMM, like everything is the source and also everything is the destination, because you're trying to compute the effect of everyone else on you. But then there's a, like on the flip side, it'd be like you would be participating in the effect on someone else. Can you read the question? I'm not sure if I answered it.
So in this case, it would be like the effect, you calculate the effect of B on every point in A. So like.
Yes. So yeah, you calculate the effect of B on every point in A, but you approximate A and B with 1 single point.
Well, the approximating A would only be for calculating the effect of A on B.
No, it's also for calculating the effect of B on A. Like you calculate, yeah. So this is different, which is you boil B and A down both to 1 point. You calculate the effect of the single point C sub B on the single point C sub A, and you just add that back to everyone else in A. Yeah. So you can see like there's a very loose approximation, but actually, it actually mostly works out, because if things are really far away, this is close enough. And the thing that I was talking about the expansions tries to fix like, in reality, maybe this is not such a good approximation, so you keep more terms. Yeah, so this is just the one way to view this approximation, which is if you had a matrix, like I said, like it's just a matrix vector multiply. And if you had a matrix where the matrix was just restricted to I and j, where x sub I was in your box A and x sub j is in your box B, and you restricted your vector to everything in B, you could, the exact version would be a matrix vector multiply of this matrix with vector. The low rank approximation is you just approximate it with 1 single value g on the center C sub A and C sub B, and you just multiply with all one's vector. You still have f of j. This is fine. This is just your input. Yeah, and the weird thing about this is that, like I was saying, every point is both the source and the target. Okay. So we have already talked about the hierarchical decomposition, but this is the second main step in the FMM, which is that you cut it in like the quadtree, and such that when you get to the leaves, every leaf contains order 1 number of points. And this is, of course, height log n if your points are evenly distributed. So this is just the same thing. You have endpoints. You have log base 4 levels, because every level cuts you down into 4 quadrants. The number of boxes on sublevel L is 4 to the L, and the total number of boxes is order n. Okay. So in the FMM, close boxes are just your neighboring quadrants in this quadrant decomposition, and far boxes are everything else that does not neighbor, that is not a neighbor to your box at your particular level. So let's just do this from the top level down. Well, level 0 and level 1, it's not interesting because in level 0, everybody is in one box. So there's no far box or no near box, just everybody's in the same. And so it's basically the same in level 1 as well. Like you cut it into 4 quadrants, but everybody is neighbors for everybody else. So you can't say that, you can't use the far approximation for level 1 as well. But luckily we have more than 2 levels. Okay, so suppose that we are computing the effect of, yeah, so we are computing the effect of box B to box A. And we can do this 3-step approximation. White in this picture is near approximation, or is near, so we cannot use 3-step approximation. These light gray boxes are well separated from B, so we can use this far approximation. So we are, yeah, it's a bit hard to get the directions right. Here we are computing the effect of B on A, where A is concretely that box, but it's true for all those light gray boxes. So we just compute far approximation for every single one of those light gray boxes. Okay, great. But we're missing what happened in these white boxes. And so now we need to go one level down in the recursion. Okay, so suppose that we're trying to compute the effect of this box B prime on this box A prime. And we get a similar story, which is that all these boxes here are far, and we have, in our pre-computation, we have computed like the center of mass. So we do this 3-step approximation of affecting, like the effect of B prime on all these A primes, denoted by light gray. And we don't need to do these dark gray ones because we have already done those one level up. And this is one of the keys as to why the FMM takes order and time, because at every level, the number of neighboring boxes, or the number of boxes that you spawn, like, okay, so you had 9 boxes one level up. That becomes, however many boxes? 36 boxes, right? Because you had 3 by 3. Yes.
Is the optimization here that you're like reusing for more approximate calculations?
Yes, you're not reusing them exactly. You're doing different approximate calculations, but you don't. The insight is that you don't need to. You have already done an approximate calculation for these boxes, so you don't need to redo like the influence of this one on these. You just need to do previously like these. All these gray, light gray and white were all white in the one level up, but since we went one level down, like now the boxes became smaller, and the set of neighboring boxes has also become smaller. So these were all neighboring. Like if you remember, this was B one level up, and these were all neighbors to B, so we couldn't use far approximation. But now when we go one level down, these are all neighbors of B prime, and these are all now we can use the far approximation. And because it was 3 by 3 before, and you cut each of those in half, that's going to be 6 by 6, which is 36. And the maximum number of neighboring boxes in this level is 9, because you have the center and you have the 8 around you. So the maximum numbers, they call it an interaction list. The maximum number of far calculations that you're going to have to, or like the maximum number of near calculations that you couldn't do is 9. And the maximum number of far calculations that you can do now is a constant number, is 27, which is just 36 minus 9. Yeah, so this is why it's order n, because it's order 1 at every level. Or order 1 is doing a lot of work in the asymptotics. And then the same story happens one level down as well. So this happens at every level of the quad tree. So now what was light gray before, like these were light gray before as well, but now you don't need to calculate on them because we have already done that one level up in the quad tree. And now, like a similar story, V double prime is now this tiny box, and then these are the neighbors of V double prime, and gray is all around those. So like the insight is at every level of the quad tree, what is defined as like well separated or far, it's fixed at every level, and you don't have to recalculate what was well separated in a previous level. And then suppose that this is a leaf level, then we can just do direct calculation on the remaining white boxes. And because we cut the quad tree such that the leaves each have order 1, again, this is order 1. Mm-hmm.
You don't still need to do this for, but so you need to do this for every like box or point, right?
Yes, you need to do this for every box. So you do the far approximation for for all the points in the box until you get to the leaf level.
Just like sum up all the levels.
Yes, you just sum up as you go down the levels. But the thing that differentiates the things within the box is, so like everything up to this point, everything up to the leaf level is just on a box basis. It only has to do with the quad tree nodes. And at the bottom level, like the differentiation between the points is through the exact computation. Yeah. So putting all those things together, the first step is you have to compute the total mass for every one of those. For every box F and B, you have to calculate this total mass, which you just add up the forces. And the second part, so this is like the main core of actually kind of doing it, which is you go level by level and you do this far approximation. So notice that it's not point by point, it's just box by box at this stage. And for every level from level 2 up to the leaves, for every box at the level 2, and then for every A in the interaction list, which is like the 27 that were not close to you at that level, you just do this far approximation. Finally, the next step, we have computed this. So this U sub A is just the effects of the effects on box A from box B for every pair of boxes, and then you add them onto the individual points. And then the last step is at the leaves, you do this direct interaction for all the things that were neighboring you that you could not do the far approximation on. Mm-hmm. The step 3 is, I guess these could all technically be, these can maybe, anyway, step 3 is, this is calculating the box-box interactions. And then step 3 is you have to propagate those box-box interactions onto the points within the boxes. So like if you remember this thing, step 1 is like this. Step 2, yeah, step 2 is like this. You're just pushing down like the sum, and then step 3 is like this, pushing it back onto the points. Mm-hmm. Okay. Does this make sense? Are people good? Mm-hmm. Yes. Oh, sorry. This is just neighbor. Oh, shoot. This is neighbors of B. Yeah. Sorry. This is your direct neighbors. Okay. So let's analyze this. How long is it going to take you? For each box in the tree, we had to compute the sum of boxes. For a given level, there are 4 to the L boxes, and this many points in this. So every level is going to take order n, That's n log n total work. The second step, which is like this thing that looks pretty complicated, that you have to iterate through the levels one by one, is actually surprisingly order n, because for a given level, okay, so remember this is what we're doing, we're going level by level, and for every box at some level, we have to calculate the interaction, the far interaction between like the faraway boxes onto this particular box. For a given level, there are 4 to the L boxes. Each one has order 1 neighbors. And so the work to do this approximation, assuming that you have already pre-calculated the force of each box, is you just sum up over the levels, this thing that's order n. So like it's just powers of 4 growing up until log base 4. And we know that's just order n. This is cool. Yeah. Mm-hmm. Yes, yeah. So there are constants being swept under the rug, but it is in a big O sense order n. Yeah, but it's unlikely that you would get height 10 in your country. That'd be a huge number of points. So, I don't know, log 4 grows pretty slow. Yeah. Yeah, so in a big O sense, this is order n. So if we were to analyze this, so we analyze the first one, there's n log n. Analyze the second one, that's order n, even though it looks like the most complicated step. To push, so this is like kind of, if you imagine like it's kind of coming up to pre-compute the forces. This one is pushing down like back into the boxes. So this is just the reverse, which is n log n as well. And then this last one is just order n, because you have n leaves, and each one has a constant number of neighbors. So that's order n. So the total time would be n log n, and then we sum up like just by adding them all up. Can we do better? Well, yes, because I promised you that this was going to be order n in total. And the way to do this, I kind of said this in the beginning, which is like if you're smart and reuse the computation from your children, then you can avoid recalculating. Like the analysis that we just did, which said that the cost of this step is n log n, it was based on like at every level you have to do n work and you have log n levels. But you could do it smarter, which is if you do it in a bottom-up fashion, it takes you order n to compute the forces for every leaf. Like you just sum up all the forces in the leaf, and you go one level up, and you have to do a constant amount of work to combine all your children's. And then one level up from there, similar story. Like you have, this relies on you having already computed this sum for all your children, but if you have, then you just combine them like this way. Just set them up. And this is just a graphical representation. The sum of this entire box B is just the sum of B1, B2, B3, B4. It takes you order 1 cost to do each of these nodes. There are order n of them, and that's order n in total. Oh yeah, F is just like, you can think of it like the force. You can think of it as like the mass that we had in barn set. Like the total, we're trying to compute like the total mass. Or this also center of mass, depends. Center of mass can also be computed this way, like it's a weighted average of your children. This is just the mass, so it's not weighted, but you would use something similar for the center. Yeah. So this depends on you being able to traverse the quadtree bottom up. But that's pretty easy. Like even if you just had a pointer to the top, you go to the bottom, which is order n work, and then you come back up. So that is order n. You could use this trick also in Barnes Hut, but it wouldn't really save you from the n log n in Barnes Hut, because like the way that you do the actual simulation, this is just in the pre-computation part. The way you do the actual simulation is along the paths. So this is kind of like in some way, you can think of it as like a smarter way to leverage like the quadtree. And then you have a similar story. Like we had two kind of symmetric steps. One was this force, like this averaging in the pre-calculation, and the last one or the third one was you have to push. Once you do this one step, three-step approximation, you have to push like the approximation into all the points in that box, and you can do the same thing, just top down instead. You push down to the children. So it's exactly the same, but in reverse, and that reduces that step as well to order n. So now we have the ability to do the FMM, which is um, step one. The only things that have changed are step one and step three. Like step two, which was the actual going over the interaction list and the neighbors, that part stays the same. And step four, which was doing the near calculations on all the leaves, that part is also the same. The things that have changed are this pre-computation of the forces and this pushing down of the results. This is like this is the faraway approximations, and this thing pushes down the results of the faraway approximations into the individual points. And all we did was change those things to be more efficient. So now, in a big O sense, they're all order n, and the total time is order n. I guess one thing that this is hiding is we talked about quad tree construction. If your quad tree construction is n log n, maybe it's like if you count that here, but you can you might also say it's fine because you just do the quad tree construction like once up front in the entire simulation, and then you run this thing at every step of your simulation. So in total, like the quad tree is going to be much less than the total time. But if you just ran one step, then the quad tree would ruin your time. Mm-hmm.
How do you, so I know these like gravity simulations often possible kind of image on one spot and like stuff together.
Mm-hmm.
In that case, wouldn't you have to remake the quad tree because then you won't have overflow in each box?
Yes, it depends. Yeah, it depends on the simulation. The easiest way is you just rebuild the quad tree every time, which may not be very efficient because like the easiest way to do is n log n time. Um, Depending on how much things move, like you could move individual points between the leaves. Yeah. And maybe that would probably because like it would take at most log n time to move any point because you have to go like up and down in the dumbest way. Or you could just use like log n to find the source and the dest, and then you just move them. And ideally, probably fewer than n points move at every step of your simulation, or fewer than n points move boxes in the quad tree. Like they all move, but they may stay within the same box, and so you don't need to change their location in the quad tree.
Which step would that happen during? Quad tree
That is not pictured here. This is just doing the actual force calculation.
like a single step.
Yeah. So like if you remember,
So to actually use this in practice, it wouldn't be overend because you want to do multiple steps.
yes, it's order n per step. So like if you remember this very high level picture, that was just doing this thing, like this for I up to n, compute this force of I. These two things are what the FMM or Barnes hut is doing. These things are not affected, which is like, well, you have several time steps, and then also once you have computed the force on every point, maybe you have to move it, like you were saying. That is not also not counted in this. That we're just doing the actual force calculation time. Yeah. I mean, the time to actually apply the forces would be order n, because like once you know the forces already, like you just move it according to you have like acceleration and you have position and you just move it. But actually maintaining the quad tree is a separate and also interesting area of study for sure. Yeah, okay, so we did this. Yeah, so now this is all order n. And then so far, oh shoot, I have 2 minutes. Okay. so far we had 3 main ideas, and I said that there are actually 4 main ideas. And one thing that I didn't talk about at all is about the accuracy. So I kind of, well, I talked about it very briefly, which is like you have this epsilon parameter, and the intuition about the epsilon parameter is rather than just 1 point of the total mass, which is a very loose approximation, they do some expansion and calculate the mass distribution rather than. So it's something about like Taylor expansions, which maybe is too deep math to do right now. But the high level idea is that rather than a single point, you compute an expansion and you keep some terms of the expansion, and the terms of the expansion can combine. The nice thing about them is that you basically keep a set of coefficients, and the nice thing about those is that they can combine in the same way that the single point does. Is from our perspective, it doesn't matter exactly what the terms are. Like there are people know them, and we could easily find them out. From a computational perspective, it just matters that you keep more than 1 point. You keep more than 1 point for the approximation, and that improves the accuracy. Yeah. So this is just saying kind of like the same thing. F sub b is a compact representation of the charge for b, which is like previously we were just doing one single point, F sub b. And then similarly, U sub A is a compact representation of the effect on the box A. But in reality, that like a single point is a very loose approximation, and we want to do better approximation without paying too much. And this is what I was saying here. Like in Barnes Hut, the number of boxes changes as you do the evaluation because like it depends on your theta. In FMM, your parameter is epsilon, and epsilon determines how many terms of this expansion you keep. So like the actual box interactions are always fixed in the FMM according to the quad tree. But the thing where like we had to combine, we had to do this one-step approximation. Like rather than order 1, now it's going to take order p, where p is log 1 over epsilon, because that's the number of terms. So like you combine, it was order 1 because we only kept the first term in some sense of this expansion before, but now for better accuracy, you keep more terms, and now it's going to take you however many terms you have to combine them. Yeah. And if, again, the big O is doing a lot of lifting, if P is order 1, then the whole thing is still order n. If epsilon is a constant, that thing is a constant. Yeah. I'm out of time, but just to summarize really quick, this, sorry, not FFT, FMM. Requires 4 main ideas. One is low rank interaction. One is hierarchical decomposition, reusing the computation, which is like the smart use of using the children computation or parent computation, and then more accurate compact representation of expanding the terms. And then so far, for ease of use, we assumed that all the points are uniform, but like you said, sometimes they can all combine into the center. If they're not, there are also adaptive algorithms available. Thank you. We can finish next time. Thanks.